Well, I think we have time enough for one quick example, so let's take a look at this one. Here we have a 5 microfarad capacitor, so we know the capacitance is charged to 10 volts, so I know its initial voltage, and so it will have an initial charge as well. So it's a charged capacitor. And then it's connected across a 10 centimeter piece of copper wire with a 2 millimeter diameter to discharge it. So we're going to use the copper wire. Um, and the question is find the time it takes to have the voltage drop from its initial 10 volts to 10 millivolts. I'll lump all of the resistance of the copper wire into R. I use the usual formula that when I charge the capacitor, I had current going this direction, so that'll be my sense of positive current flow. Now, obviously, when I close the circuit, then I will get the charge flowing off of it. But I'm really interested in just the voltage drop across this capacitor as a function of time. And I know the voltage drop across the capacitor is just the charge on the capacitor divided by its capacitance. And I know that for the discharging case, the charge on the capacitor is its initial charge, and it dies off exponentially. So for Q of t, I've got Q naught e to the minus t. And then Q naught over C, well, that's the initial voltage that's on it. So I get the voltage on the capacitor at really any time t is its initial voltage times this exponential factor. Well, I put in what I know. I know that at time t equals 0, it was charged up to 10 volts. And then I have this, I really have the voltage at any time t. It's just going to be 10 volts and it decays exponentially. But I want to know the specific time in which the voltage is 10 millivolts. So I want this side to be 10 millivolts, and that'll occur when the time t satisfies this equation here, just putting in the 10 millivolts there. And then what I did was I solved for the exponential factor. It's just going to be the 10 millivolts divided by 10 volts. And so this exponential factor has to become 10 to the minus 3. And then what did I do? Then I took the natural logarithm of both sides of this. So I get the natural logarithm of e to the minus t over t. Natural logarithm and e are inverse of one another, so I just get the argument of this side, minus t over tau. And if I took a natural log over here, I have to take a natural log on this side as well. And when I calculated the natural log of 10 to the minus 3, I got minus 6.91 for my calculator. Notice the two minus signs go away. And I can solve then for the time t in terms of the time constant. It's going to be 6.91 time constants. So now it really just becomes calculate the time constant. We were given C, it was 5 microfarads, but we weren't really given the resistance. What we were given was the length of wire and its diameter, and it was made out of copper. So we need to use the resistance relationship for a length of wire cross-sectional area A. In this case for copper wire. Since it gave me the diameter, and usually I remember the area of the cross-sectional area in terms of radius, so the area is pi r squared, where r is half of that diameter that was given. When I looked up the resistivity of copper, I had found 1.7 times 10 to the minus 8 ohms times meters, or ohm meters. L was 10 centimeters, or 0.1 meters. Pi, and then the radius, the diameter was 2 millimeters, and so the radius would be 1 millimeter, or 10 to the minus 3 meters. And if you work all of that out, the meters squared on bottom will cancel the meters squared on top, and I got 5.41 times 10 to the minus 4th ohms for the resistance of that copper wire. And now then I can find the time constant, because I have to come up here. That's R times C. It's the resistance, 5.41 times 10 to the minus 4th ohms, times 5 microfarads, or 5 times 10 to the minus 6 farads. And if I do all of that, I get 2.71 times 10 to the minus 9th seconds for the time constant. And then from above, the time at which the voltage is 10 millivolts was 6.91 time constants. So 6.91 times our time constant, and I get 1.86 times 10 to the minus 8 seconds. Or I'd probably write that as 18.6 nanoseconds. So about 19 nanoseconds. So very, very rapidly it will discharge in this particular situation.